Good morning to one and all. So in this session number 10 we are going to discuss about power efficiency of power amplifiers. So this comes under the topic BJT biasing and amplifiers. Now what are the topics we are going to discuss today here is class A and class B amplifiers, output power expression, maximum efficiency calculation, and what will be the maximum possible theoretical efficiency of class A and class B amplifiers. Okay, we already know that the power amplifiers are classified into several types. I think in the previous sessions and all you have studied about classification of power amplifiers. So in this particular session we are mainly discussing on or mainly concentrating on class A and class B power amplifiers, their efficiency calculations. So what is the meaning of class A power amplifier? The class A power amplifier is nothing but the conduction angle of class A power amplifier is 360 degree. What is the meaning of 360 degree conduction angle? The conduction angle is 360 degree. It means that the active device in an amplifier conduct for complete input cycle. Now which is the active device? In case of power amplifier, the active device is transistor. So the transistor will conduct for complete half of input cycle. So that's why they mentioned here in class A power amplifier, the active element, that is transistor, conduct for complete cycle of input signal. Now what is the conduction angle? The conduction angle is 360 degree in case of class A power amplifier. Now where exactly the operating point is located? I think you have studied about DC load line. So in a DC load line concept, we have to calculate what will be, we have to identify where the Q point is located on the DC load line. Now for every amplifier we are classifying based on the position of Q point also. That means where the operating point Q point is located. So based on that we are going to calculate, we are going to identify which type of amplifier it is. Now coming to this particular session, we are discussing about class A power amplifier. So in class A power amplifier, if the conduction angle is 360 degree, then the Q point, whatever we are saying, the Q point is located in the middle of the DC load line. So what exactly it indicates? That means you will have a DC load line. The Q point is located at the middle of the DC load line. So then whatever the input waveform will be there, complete it will be appear at the output side. So that's why the three very important point, the active element is conduct for complete half of input cycle, the conduction angle is 360 degree, and where the operating point is located, operating point is located at the center of the DC load line. Now this is series fed class amplifier, class A series fed amplifier. So here you can see in the diagram there is one active element, that is called transistor, is present, and C1 is nothing but coupling capacitor. Now what is the meaning of coupling capacitor here? Means this will block the DC input voltage and it allows only the AC input voltage. And coming to next one here, this is also called as direct coupled amplifier. So why we are calling it as direct coupled amplifier? Means we are taking the direct output from the resistor itself. That means at the collector end we have connected a resistor and we are taking the output directly from the resistor. So that's why this is called direct coupled series fed amplifier. Now in the right side of the slide, the diagram whatever it shows, it's output characteristics. You can observe the output characteristics there. So in the output characteristics, where the Q point is located, Q point is located at the middle of the DC load line. When the Q point is located at the middle of the DC load line, what will happen if you observe the input signal, sinusoidal signal? Now the input signal is for 360 degree, and at the output side also you can observe there the output signal is also for 360 degree. Now the output signal, why the reason output signal appear for complete cycle of input signal? Because of the position of Q point at the center of the DC load line. If you shifted the Q point upwards or downwards, the waveform at the output side, it may not be complete 360 degree. Either it will be less than the 360 degree. So if you shift the Q point a little bit downwards, then now that's why the Q point position on the DC load line is very important. Now conversion efficiency. See, every power amplifiers, we are classified the power amplifiers based on one of the factor that is called conduction angle. And second one is here conversion efficiency. What is the meaning of conversion efficiency? See, for a transistor and all, we are calling it as gain. Whereas for power amplifiers, we are giving a name as conversion efficiency. What is the meaning of conversion efficiency? Means there is a general law, that means energy neither be created nor be destroyed. So same concept here, the amplifier, power amplifiers, what is the input signal we are applying? For power amplifier, we are giving a DC input power supply. Now this power amplifier, what it will do? It will convert the input DC power to output AC power. Now how much input DC power supply you are applying? For that particular value of DC input, what is the percentage of voltage it is converted into AC? That means that is called conversion efficiency. Here we are saying it is the measure of ability of power amplifier. That means what will be the ability of power amplifier to convert the DC power into AC power. That means how much ability the power amplifier has to convert the DC supply into AC supply. We are calling it as conversion efficiency. The efficiency of power amplifier is defined as AC power delivered or transferred to the load. That means at the output side, in the previous slide you have studied about the load resistance RL. So at the load resistance RL, what is the amount of AC power you are delivering? From what? From the DC power supply. That means from the DC power input. So that is called maximum conversion efficiency. And mathematically we can express it as the conversion efficiency is equal to AC power input divided by DC power taken from the biasing supply. That means what is the DC power you are applying for that particular DC supply, what is the AC output it is produced. This is called conversion efficiency. This is equal to PAC divided by PDC into 100. So why you are multiplying by here 100 here is equal to, because we are expressing the efficiency in terms of percentage. So what is the conversion efficiency? Conversion efficiency is nothing but the ability of power amplifier to convert the input DC supply into AC supply. What will be the ability? Now what is the DC input power? Now we already mentioned the DC input power we applied during the biasing supply. That means the DC power input provided by the supply with no input signal. When you are not applying any AC input signal, what will be the DC supply you are providing? That is for biasing purpose. So that DC current drawn is at the collector end. That means when you are applying a biasing voltage, what will be the current which flows across the load resistance RL that is connected to the collector end. So the load resistance RL is connected to the collector end, and the amount of current flows across the load resistance RL, and that is when we are calling it as ICQ. It's a collector current. So we know the general expression for power. Power is equal to voltage into current. So P is equal to V into I. So that's why PDC is equal to VCC into ICQ. So this one we are using to calculate the conversion efficiency. Now coming to the DC load line. Now I think you have studied this one, DC load line concept. If you observe the graph, in the graph where exactly the Q point is located? Q point is located at the center of the DC load line. Now if you calculate the distance above the Q point and below the Q point on the DC load line, it is equal. So that's why we are saying it is at the center of the DC load line. and you have to calculate the coordinates or Cartesian, the points of Q point, the values of x-axis and y-axis at Q point. So x-axis is nothing but VCE, voltage across collector and emitter junction, and y-axis is nothing but IC, that is current through the collector. It's a collector current. Now what is the values of x and y coordinate at Q point? We have to calculate. Now if we observe the voltage waveform, so voltage waveform, what is the maximum possible amplitude? The maximum possible amplitude is VCC. Now where exactly the Q point is located? Q point is located half of the VCC. That means Q point is exactly half distance from the VCC. So that's why the Q point I am writing it as VCC by 2. See, again I am repeating, the maximum amplitude is VCC and Q point is located at the center of the DC load line. So that's why the Q point corresponding value of VCE at Q point is equal to VCC by 2. At the same time, if you observe on the current waveform, the maximum possible amplitude of the current is equal to VCC by 2. VCC by RC, VCC by RC. Now where exactly the Q point is located? Q point is located at the half of the DC load line. So that's why the corresponding value of IC with respect to Q point is equal to VCC by 2 RC. So the operating point Q is equal to Q VCC by IC, or ICC is equal to VCC by 2 RC, half of the VCC by RC, and maximum voltage is VCC. So Q point, what is the value? VCC by 2. Yes. Now we know that Vm is equal to maximum voltage amplitude, and V peak to peak is nothing but peak to peak voltage of voltage signal. So that's why the maximum value is nothing but peak to peak divided by 2. Now how we can express peak to peak value? Peak to peak value is nothing but maximum value minus minimum value divided by 2. That means V peak to peak is equal to maximum minus minimum, whereas Vm is equal to, either you can write it as V peak to peak by 2, or you can also express it as V maximum minus V minimum by 2. Next, what is Im? Im is nothing but amplitude of AC current. But at the same time, similar expression, amplitude of AC current, either you can express it as I peak to peak by 2, or I maximum minus I minimum divided by 2. Now what is the RMS value? The RMS value, if I am expressing the maximum voltage and maximum current in terms of RMS value, then Vm is equal to Vrms by 2 and Im is equal to Irms by 2. So Vm is nothing but maximum amplitude of waveform, Im is nothing but maximum amplitude of current. See, these maximum amplitude of voltage and current, if I am expressing in terms of RMS value, then Vm is equal to Vrms by 2 and Im is equal to Irms by 2. Then according to Ohm's law, everyone knows that V is equal to I into R. This is a standard expression. Voltage is equal to current multiplied by resistance. Now here we are calculating the Vrms in terms of I and R. It is equal to Irms into RL. R is nothing but load resistance which is connected across the collector end. Now at the same time, Vm is equal to Im into RL. Now how we can express the peak power output? So the peak power output, PAC, either you can express in terms of maximum amplitude. Now the peak output power we can also express in terms of Vm and Im. So that is equal to PAC is equal to Vm into Im. Now if I am expressing Vm into Im only in terms of Im, then I will express it as Im square divided by Im square RL by 2. Now if you observe about here, now why I am getting here Im square by Im square RL by 2 means this Vm, here I am taking V I am expressing V I am expressing in terms of I into R. So that's why this will become Im into Im RL. Now by 2, because here I am taking root Vm by root 2 Im by root 2. So that's why I am getting Im square RL by 2. At the same time, if you are expressing power only in terms of voltage, then it will become Vrms square divided by 2 RL. Now if I am expressing in terms of peak to peak value, so PAC is equal to Vm Im by 2, because there Vm by root 2 Im by root 2, if I am multiplying, then it will become Vm Im by 2. The 2 factor why I am getting, because root 2 I am multiplying. Now what about Vm value? So the Vm value, if I am expressing in terms of peak to peak, then this will become V peak to peak by 2, Im is equal to I peak to peak by 2 whole divided by 2. So the PAC is equal to V peak to peak into I peak to peak divided by 2. So now if I am expressing in terms of only current, then it will become I peak to peak square RL by 8. If I am expressing only in terms of voltage, then it will become V peak to peak square divided by 8 RL. Now how you will express the efficiency? The efficiency expression, while calculating the efficiency of power amplifier, what you are going to do here? Now you are expressing the PAC. PAC is equal to V maximum minus V minimum divided into I maximum minus I minimum divided by 8. Now this V peak to peak I am replacing by V max minus V minimum. I peak to peak I am replacing it by I max minus I minimum. So while calculating the efficiency of efficiency expression, we have to use AC power as well as DC power input. AC power output we have to use, as well as we have to use DC power input. Now what is AC power output? The AC power output is V maximum minus V minimum multiplied by I max minus I minimum divided by 8. This is what AC power. Now what was the DC power? I think recall the earlier expression whatever we use. So the DC power is equal to VCC into ICQ. Now to calculate the efficiency expression, so the AC power output divided by input DC power. So what is the output AC power? Output AC power is equal to V max minus V minimum into I max minus I minimum divided by 8 VCC into ICQ. If you recall the equation number 1, while calculating the DC power input, there we use PDC is equal to VCC into ICQ. And again why we are multiplying here by 100? Because we are expressing in terms of percentage. So that's why efficiency is equal to V max minus V minimum into I max minus I minimum divided by 8 VCC ICQ. Now what is maximum efficiency? So the maximum efficiency is calculated as what will be the maximum swing of both output voltage and current waveform. That means this is depends upon the DC load line Q point again. So if the Q point is located at the center of the DC load line, what will be the maximum swing of voltage and current? Now if you go for the previous slide, I think where I explained about DC load line, no? Yes, here I explained about the DC load line, there Q point. If you observe what is the maximum voltage swing, the maximum possible voltage swing is VCC. And what is the maximum current swing? So the maximum current swing point, see if that's one I will express in terms of ICQ. Now at Q point what is the IC value? At Q point IC value is ICQ. Now at the maximum value of this one current Im, if you observe the Q point, this is double that of that one. So that's why I am expressing it as 2ICQ. So the maximum voltage swing will be Vm is equal to maximum voltage swing will be VCC, and the maximum current swing will be 2ICQ. And what is the minimum voltage swing here? The minimum voltage swing is 0. V minimum is 0. And what is the minimum current swing? the minimum current swing is also 0 here. So that's why I minimum is equal to 0 and V minimum is equal to 0. Whereas V maximum is equal to VCC and I maximum is equal to 2 ICQ. So that's why the value of V and I for maximum swing we are calculating as V maximum is equal to VCC and V minimum is equal to 0. I maximum is equal to 2 ICQ and I minimum is equal to 0. Then using the power this is using the equation, this is not PAC, it's a percentage, it's a eta, that means maximum efficiency. So that is equal to V max minus 0 because V minimum value is 0, I max minus 0 divided by 8 VCC ICQ. Now what is V maximum value? V maximum value I will write it as VCC. What is I maximum value? I maximum value I will write it as 2 ICQ. So VCC ICQ get cancelled, multiply by 100. So finally it will become 1 by 4 multiply by 100, that is equal to 25%. What exactly it indicates 25%? The 25% indicates that the maximum possible theoretical efficiency of direct coupled class A amplifier is 25%. That means the input DC power supply, whatever you are applying, 25% of input DC power is converted into AC power. So this is the class A power amplifier efficiency. If you are going for class B power amplifier, the active element conducts for 180 degree of the 180 degree. That means the conduction angle is 180 degree. The active device, that means transistor, is on for half of the input cycle. In case of class B amplifier, the active device, that means transistor, on for half the input cycle. And where exactly the Q point is located? The Q point should be located at the cutoff region, approximately at the cutoff region. When the Q point is located approximately at the cutoff region, what will happen? The positive half circle will be appear at the output side, whereas the negative half cycle will be clipped off. So this is what class B power amplifier, half of the output will be appear as a input cycle. Input cycle, half of the input will be appear as a output. Now in case of class B power amplifier, how will you calculate the DC power input? We have to calculate the IM value or average current. So what will happen, if you observe the class B push-pull amplifier, there are two transistors are present. So upper transistor and lower transistor. So or else if you are taking complementary symmetry, you will have one NPN transistor and second one is PNP transistor. Now what will happen in class B power amplifier? The Q point is located at the cutoff. When the Q point is located at the cutoff, whatever we are applying input signal, it will produce only half cycle. Now when each transistor is producing an output that is similar to half wave rectified output. Now recall the expression of half wave rectifier, what you studied in the earlier classes. So the rectified output, the average current, if IM is nothing but peak current, IM is nothing but peak value of current, then the average current or DC current I will express it as IM by pi in case of rectifier. Now here also in class B push-pull amplifier, we are using two transistors and each transistor is producing an output that is similar to half wave rectified output. So that's why what we are doing here, we are taking the average current is nothing but contribution by two transistors, with each transistor producing an output similar to half wave rectified output, that is called IM by pi. So that's why we are calculating the total DC or the average current IM is equal to IM by pi plus IM by pi, that is equal to 2 IM by pi. See, this value is similar to your ICQ value. So here this one I will use in a expression while calculating the efficiency, that is equal to IM is equal to 2 IM by pi. Now output power calculation. Now for output power calculation, as I already mentioned, the class B power amplifier conducts for half of the input cycle. That means the conduction angle is 180 degree. It is clear from the output value here that the VCE value and IC value at output current has the peak value of IC sat. Now where the Q point is located, if you observe the Q point, where the Q point is located, Q point is located at the center of the at the cutoff region, approximately at the cutoff region. Now approximately at the cutoff region, what is the VCE value? That means voltage across the collector and emitter terminal. What is the value? That value will be VCC by 2, and current will be 0 at that particular position. So that's why IC value I will express it as 0, and VCE value will be VCC by 2. See, this Q point is very important when we are calculating the power efficiency and all. Now the RMS value, if I am expressing in terms of maximum value, then Vrms is equal to Vm by root 2 and Irms is equal to Im by root 2. That means I am expressing the Vrms value in terms of maximum value. So the AC power output can be calculated as PAC is equal to Vrms into Irms. Now we know that Vrms is equal to Vm by root 2, Irms is equal to Im by root 2. So that's why the PAC is equal to Vm Im by 2. Or else, if I am expressing the power in terms of voltage and current, that will be Vrms into Irms. Suppose if I am expressing the power only in terms of current, then it will become voltage, I can express it as I into R. So that's why it will become I square R. Or here I will call it as V square RMS into RL. If I am expressing the AC power only in terms of voltage, then I will write it as V square by RL. So here I will write it as V square by 2RL. Actually this will become 2RL. So while using the peak value of AC power output, if I am expressing the AC power in terms of peak value, then it will become Vm Im by 2. Or if I am expressing only in terms of current, I square M RL by 2, or only in terms of voltage, that is Vm square divided by 2RL. Now how will you calculate the efficiency? The efficiency of class B power amplifier can be calculated as like similar expression we use for class A also. So the conversion efficiency of class A, while calculating, what we use the formula, that is equal to PAC divided by PDC. That means output AC power delivered or transferred to the load divided by input DC power. That means how much AC power you are applying, how much AC power you are getting at the collector end, divided by what is the DC power input you applied, multiplied by 100. Now what is the PAC value? I will take the output power AC value only in terms of maximum value, then I will express it as Vm Im by 2. Now what is the DC power input? The DC power input, we know that it is equal to VCC into ICQ. Now this VCC I will keep it as it is, whereas the ICQ, that is nothing but average or total DC current, here I will consider it as ICQ is equal to 2 Im by pi. So why I am taking 2 Im by pi? As I already explained, in case of class B push-pull amplifier, so each transistor produces an output that is similar to half-wave rectified output. So that the rectified output output current value, average current I will express it as Im by pi. So that's why here ICQ I will express it as 2 Im by pi. So that's why this will become Vm Im by 2 divided by 2 pi VCC into Im. So here Im get cancelled. So now it will become pi by 4 Vm by VCC multiplied by 100. Now for again, this is the efficiency formula. Now this one I need to calculate for maximum efficiency. So the maximum possible efficiency means what will be the maximum possible swing of input voltage. Now output voltage here. Now the maximum possible allowable possible swing of output voltage Vm is equal to VCC. So then that means in place of Vm you have to put VCC value. Now the percentage of efficiency is equal to pi by 4 VCC by VCC into 100. It will become 78.5. Now what this 78.5 numerical value significantly indicates? So this numerical value 78.5 indicates that the maximum possible theoretical conversion efficiency of class B power amplifier is 78.5%. That means whatever the DC input you are applying, 78.5% of DC input is we can convert into AC power. So if you are compare the class B with respect to class A power amplifier, so in terms of efficiency we can say that yes, class B power amplifier are superior in compared to class A power amplifier, because if you are applying a 40 units of power as a DC supply, in case of class A amplifier only the output AC power will be 10%. That means 10 units of AC output will be produced. Whereas in case of same 40 units of supply, we are DC supply, we are giving it to class B power amplifier, it will produce an AC output similar to 32 units. That means approximately I am considering it as 80%. That's why I am saying approximately 32 units. That means there is a lot of improvement in the conversion efficiency of class B power amplifier as compared to class A power amplifier. Now let's discuss about the multiple choice questions which are relevant to the sessions what we discussed till now. So the first question, the maximum efficiency of resistance loaded class A power amplifier is. Now the resistance loaded class A power amplifier, I think you people can guess the answer. These topics are we discuss. What will be the efficiency of maximum theoretical efficiency of class A power amplifier? So the answer here is 25%, because 78.5% is its class B amplifier. Next, in class A operation, the operating point is generally located. That means what they are saying, in class A power amplifier, where the Q point is located on the DC load line, we have to calculate. So recall the things what we discussed in the DC load line calculation, as well as I mentioned while calculating the power efficiency also. Class A power amplifier, the conduction angle is 360 degree. So conduction angle is 360 degree means where the Q point should be located. The Q point, yes, the answer for this question is Q point is located for class A operation at the middle of the DC load line. So Q point is located at the middle of DC load line for class A power amplifier. Class B amplifier delivers an output signal of 180 degree and have a maximum efficiency of. Now this is again a direct question related to the numerical value. The class B power amplifier, what will be the efficiency? See, in the first question we calculated the efficiency of class A amplifier. So the efficiency of class A amplifier is 25%. Where in this question they mentioned class B power amplifier. Again the class B power amplifier, the Q point is located at the cutoff and we will get an output signal of 180 degree. And what will be the maximum efficiency of class B power amplifier? The maximum efficiency of class B power amplifier is, yes, the answer for this question here is 78.55%. Yes. The next question, for class B power amplifier, the operating or Q point is set at. Yes, I think I explained in the previous slide also. Class B power amplifier efficiency is 78.55%. And where the operating point is located? Yes. Any guess? Okay. Similar to class A, sorry, in case of class A, Q point is located at the center of the DC load line. Whereas in case of class B, where the Q point is located, because we have to get an output of half the cycle of input. So the Q point is located at the cutoff region, because at the center it is for class A. So the class B Q point is located at the cutoff region. Which amplifiers can be used for linear amplifications? For linear amplification, which amplifiers we are using? So for the linear amplification, we can use both class A as well as class B amplifiers. Now, amplifiers conversion efficiency are calculated using which formula? Now, how can we calculate the amplifier conversion efficiency? See, the amplifier conversion efficiency, we can also, I'll recall the things what we discussed in this session. There we discussed the conversion efficiency of amplifier is nothing but AC power output divided by DC power input. Now this one I can call it as AC power divided by DC power or dissipated power. So that's why the answer for this question is both A and B will be correct. And these thank you one and all for this session. And in the next session we are going to discuss about class AB and class C amplifier, because you know that in case of class power amplifiers, till now we discuss about class A amplifier, class B amplifier, we discuss about power efficiency of class A amplifier, class B amplifier. There we can say that class B is more efficient in case of conversion efficiency with compared to class A. Now in the next sessions we are going to discuss about class AB amplifier, class C amplifier, and at the end of the session, at the end of next session, we will discuss about the comparison of the power amplifiers and all. There we will discuss these topics again, what all the important points and all. So next session we are continue this topic of power amplifier comparison as well as class AB and class C amplifier. Okay, thank you one and all.